Hello, hello. Oh, oh, yes. Okay. Hello, hello. Here we go. All right, all right. Just hello, Karen. Thank you. Good afternoon, Samantha. Thank you. Good afternoon, Yaneli. Thank you. Good afternoon, Brandon. All right. Good afternoon, Kaya. Hello, Ariana. Where are we? Good afternoon, Erica. Good afternoon, Roger. Good afternoon, Sydney. Good afternoon, Sonam. Good afternoon, Gabriella. Awesome, awesome. All right, we are rocking and rolling here. Low on the video, but high on the chat enthusiasm. I'll take it. I'll take it. And thank you, Yaneli, for breaking up the monotony with a avatar, or in fact, an actual photograph. Although, how would I know that? It could be somebody else. But anyway, yes. Hello, everybody. All right, let's get rolling. Um, so first of all, I hope you saw on the stream. I totally apologize. I don't want to dwell on this now and lose class time but yet somehow I messed up the homework deadline. So hopefully, so all of you who managed to rise to the strange occasion of jumping the gun on the homeworks got a lot of point. If you have any questions about what I did to rectify the situation, just text me or email or chat me or whatever. But the bottom line is that what was meant to be to do today's homework 5B, um, not homework 6. So homework 6 is really not due until next week. So everybody has plenty of time to do it or to get all the points. But if you already did make a valiant attempt, then you've gotten a huge amount of the points already, like more than you otherwise would have because blah, blah, blah. So I hope, and yes, that homework, you're ahead of me. So there's going to be catch up time for us all to catch up together. Um, but today we still have to finish talking about homework 4. That is the deal. Which means there's still plenty of time. You're supposed to be doing drafts of these 5 and 6 and whatever. If you do the first draft in time for the deadline, then you get a ton of points, and then you have the ability to get all the points eventually. If you don't do a first draft for the deadline, then you can get a lot of points, but you can't get all the points. I hope that's increasingly clear to people. Um, But what we're now still going over, we're in the middle of homework 4, average acceleration. Okay, so that's where I'm going to direct my attention in a couple of moments. We're going to do a couple of problems from homework 4 where I could say we were going to finish it today. That was my plan. It's not going to get finished today. And if I have to bump up and give you even more time for the other homeworks, I will. Like I'm bearing it all in mind. But we're going to get some progress through homework 4 today. A little quick speech about the equations that you have on the, and again, stop, if there's any questions about where we are, where we've been, or where we're going, stop me and put them in the chat. But for the moment, I'm going to assume it. And I missed you Wednesday, and thank you for rolling with the whole Wednesday thing. At the end of class, like we're in the last 10 minutes, I'm going to turn off the recording and I'll explain to you why I was absent Wednesday and why I might be absent again. Why I will be absent again. I will explain that, even though it's on Zoom. But now that I've told people in person, I feel like it's so I will at the end explain what's going on with that and how I'm going to ask you to bear with me, whatnot. Uh, but for now, we're in homework 4. Excuse me. Okay. Oh my gosh. Okay, we're in homework 4, and there's 3 equations on the board here, right? And it's looking more and more like physics, maybe. And more each day, there'll be equations on the board, and it tends to be like an equation of sort of where what we just established leading toward like the equation we're trying to get at. Like that's what this is. I believe that the top equation, I mean, which is sort of really 2 equations, but the top equation of the 3, in principle, is what we kind of established in one of the earlier problems of homework 4 last Monday. We established it. I'm not saying we fully explained it. I'm not saying we fully practiced it, but it emerged. And then the central equation that was presented in homework 4 was the middle one. So we're going to spend a lot of time today talking about those 2. Now, where we're trying to get toward is the last one. The last equation will emerge from problem 6, the last problem on homework 4. It will emerge from, we'll discover it in problem 6 from homework 4. Again, honestly, actually, we're not going to get that far today. It was my hope, but it's not going to happen. So that's a future projection, that last equation. So if you don't understand the last equation, it's okay. Like you're not meant to yet. It's just where we're heading. But let's talk about the first two. Please allow me to talk about at least the first one for a bit before we start crunching numbers again in homework 4. Um, the top equation says that and you really, I would encourage you to take some, I'm not going to scribble more notes on this. I would encourage you to write down some notes on what I'm about to say. Like, like maybe start a new page, make a big box, like write this top equation by itself and get ready to write like arrows pointing toward it or things around it, commentary on it. Because this equation at the top is a new equation for V, right? We already had an equation for V bar. We had a definition of average velocity. We said average velocity V bar, like V bar triple equal sign X minus X naught over T, right? You might even want to write that down again to remind yourself. Like that's the one concept we have so far. Average velocity is change from one position to another per change in one moment to another. Displacement interval per time interval, right? That's what average velocity is. That's what we know. Now, if you want to think about that graphically for a second, and I would encourage you to do so, if you made a graph where time and maybe try this, like sketch this while I'm talking and hand it in for points. If you make a little sketch, a graph, like axes, where time is your independent, your horizontal axis, and position, so time measured in seconds is this axis, and position measured in meters is this axis, right? And then you just draw some arbitrary curve from the origin, like going up, or some wacky curve. That curve would represent what we might call the world line. It will represent the trajectory through space and time of a particle, like of a car or of a ball on a hill or a professor going back and forth on a meter stick in front of a class. Like if you picture that graph, an XT graph, the curve represents what an object is doing within one dimension of space during one dimension of time, right? So the graph might go like up and down and like it might have hills and valleys and go up, but that doesn't mean that a person is going up and down. And when the graph goes down, it means the person is travel. When the graph goes down, it means the person's traveling in a negative. Let me start again. When the graph is heading up, that no matter what, the graph is going to the right because time is ticking to the right. When the trend line, just random trend line that you just draw, just look at any random crazy curve, it's got to be going from left to right because time goes from left to in your graph goes from left to right. Anywhere in that graph that the curve is like heading up while it goes to the right, that means that the object is traveling in a positive direction. Like in homework 1, number line, it means the person's going to the right or the east or whatever, right? And then when the graph dips down, it doesn't necessarily mean anything about slowing down it just means that the particle, the person, is now traveling backwards, right? There's only one, right? And if it curves, it doesn't mean the person's making like a slow left turn or so. Like there's just forward and backwards. So up in a graph means forward while time ticks forward, and down in the graph means backwards while time ticks forward, right? I'm saying we're graphing one dimension of space with respect to one dimension of time. Now, and I would encourage you again, like make a little sketch of that. I don't want to rabbit my whole. If I start drawing it now, I'm going to take even longer to get back to but just draw it like a random sketch. T, X, random curve that goes somehow from down left to somehow up right. Now, what is average velocity on that graph? Well, I mean, if you take any two random points on that graph, like any 2 points, a point is a point in time and space. Like a point, like so two random points. Technically, mathematically, we would call them like x1 comma t1 and x2 comma t2, or in physics we might call it x naught t naught and x comma t. Same idea. Like two, each point has a space coordinate and a time coordinate. And if you look at any two random points, their on the graph you drew, the graph in between those 2 points might be a wacky curve. But if you imagine or draw in a little dotted straight line between those 2 points, if you draw a straight line between those 2 points, like a dotted one, that straight line represents not what actually happened, like there was some crazy motion back and forth, speeding up, slowing down, but that dotted straight line is the direct interval between those 2 points. If you think about it, and stop me if this is, I know this is a little bit abstract since I'm not drawing, but if you think about it, if you draw a straight line between any 2 points on a position time graph, the slope of that straight line, the slope would be the rise over the run, right? If this were a regular graph in math class and they didn't care about like space or time or anything, it was just like dependent variable. If it was just like a y-x graph in math, what is slope? It's y2 minus y1 over x2 minus x1, or in other words, delta y over delta x, right? Slope is change in the y values, or excuse me, difference in the y values divided by difference in the x values. Like in regular, if you just have an arbitrary function, y equals f of x. Well, here, we're not doing y and x, we're calling them x and t. It's all the same math, it's just that we're specifying now that this axis, we're not calling y anymore, we're calling it x, oddly. And because this axis, we're not calling it, we're calling time, because we're actually like talking about like the world now. So the slope of a straight line, the slope of any straight line that you draw, even if it's not what the graph actually did, but any straight line that you draw between 2 points, the slope of that line would be delta x over delta t, or what you might call x minus x naught over t minus t naught. And stop me if you're not following this, like really, or direct chat me. Oh, no school this Wednesday. Whoa, wait, okay, noted. I'll get back. I actually totally did not realize that. Russia. Okay, noted. I'll get back to that. Thank you. No, you're right. I didn't realize that. Thank you for telling me. Let me just keep going for a second, but thank you, Alfred. And you get points for that. There's got to be a portal for that. So slope of the dotted line, the straight line between any 2 points on your xt graph, the slope would be delta x over delta t, which in physics, i.e. x2 minus x1 over t2 minus t1. Again, if you can be writing all these things out to show yourself that I'm actually making it, like if it makes it clear, please write this all out. But what I'm ultimately trying to say is delta x over delta t, rise over run on this graph, what they would call in a math class, slope, rise over run. In physics, we're calling x minus x naught, like we could have called it x2 minus x1 over t2 minus t1. But in physics, we don't call it 2 and 1. Some people do, but we don't in this class. We call it x minus x naught over t minus t naught. But the t naught is always a 0, so we don't even bother writing it in. But like you could if it makes the whole pattern clearer to you. So what I'm saying is, a number of things. First thing I'm saying is that what we've been calling average velocity, displacement over time, if you want to think about it mathematically or graphically, average velocity, the rate at which you change position per time, is the slope of the straight line connecting any 2 points on a position time graph. That's what average velocity from physics is, the slope of the straight line connecting any 2 points on an xt graph. Average velocity is slope, as long as you're talking about position versus time. Now, what's that got to do with this equation? Now I'm talking about average velocity still. I haven't even said this equation yet that's on the board. But what I'm saying now is, wait a second. Okay. So this is why it's an average. So think about it. If you just drew a random curve as I asked you to, and now but then you superimpose a straight line on it between any 2 points, and you talk about, I'm saying the average velocity between those 2 points, like the average velocity that the car did between 3:05 p.m. and 4:05 p.m. The average velocity is whatever the slope is of that straight line connecting those 2 points, 3:05, where it was at 3:05 to where it was at 4:05. It's the slope because it's like the rate of change of it's the rate of change of position per change in time. But it's the slope of that straight line. Even though the graph is not a straight line, you just made up a straight line to connect the 2 points. So like, what does that mean physically? It means that's why we're calling it an average. Because what we're saying is between 305 and 405, on average, between 305 and 405, in total, the car went 20 miles and it took an hour. So to get the slope of that straight line is to say, oh, it covered 20 miles in an hour. So on average, it was going 20 miles an hour. That's the slope of the straight line. If it had gone the same speed the whole time, the speed would have been 20. Now the graph shows that the car didn't actually go the same speed the whole time. Like the the car wasn't traveling in a straight line, i.e., sometimes it was going slower, sometimes it was going faster, sometimes maybe it was even going backwards. I.e., if you look at the curve, the slopes of the curve, it was getting steeper, less steep, negatively steep. There wasn't just one steepness. The slope of the straight line that you make up the direct thing between the path, between the 2 points, that's on average. That's the one number that would be best to represent the whole, but it's not what it was doing any given moment, right? Like, unless the whole graph happened to be a straight line, in which case then it would be, and there's no need for all these details. I hope you're still, wait, just raise your hand if you're still with me at all, or if I've totally lost everybody either to confusion or boredom. Or probably boredom, but are you still, is it so clear what I'm talking about? Sort of? Okay, I'll take it. Thank you. You're very polite. All right, I appreciate it. All right, I'm almost done with this rant, and I'll get more concrete in a second. Where I'm going with this is average velocity, then, in short, average velocity, physics, is the slope of the straight line connecting 2 points on a position time graph, even and especially if the position time graph isn't itself straight. Whatever the straight line is between 2 points, the slope of that is the average. Now, what we all recognize, if you look at the graph and you realize that straight line is not the reality at any given point in between, that example is like saying, in real life, like when I get pulled over by the police officer and the police officer says, how fast were you going right then when you passed the school? And I say, well, I've been traveling for an hour and I only covered 5 miles in the hour. So on average, I've been going 5 miles an hour. Like that's nonsense, right? You all see, like it's the same problem as the graph. Even though what I just said is true, I've been traveling for a total of an hour since the last time point that I cared about, and I only covered 5 miles. I did all kinds of crazy stuff in the hour. And he or she, the police or they, the police officer is interested in a particular moment. And that moment is not on the straight line that I'm talking about. So what do we do? There's got to be, I was doing some speed when I went past the school and it wasn't 20 and it was a number. So there's got to be a way to talk about how fast and in what direction we're going at a certain point in time rather than on average between 2 points in time. So what we do, so there's got to be a way to be concerned with velocity at a point rather than velocity on average approximately between 2 points. So, but the problem, the difficulty is if we literally just say, okay, we'll apply the original equation, we'll just do like displacement over time when no time has passed, like we'll just plug it in for a point rather than two. Well, then we plug in 0/0 every time. We said last week, right? So if we literally just say we want to apply, if we literally want to define instantaneous velocity v without, if we want the more, we want the more precise thing. We don't just want average velocity v bar. We want instantaneous velocity at a instant, at a point. It's got to mean something. It's got to be quantifiable. We want to quantify it, but we can't be simplistic about this. If we just say, oh, it's average velocity at a point, it's however far you got in no time. Well, however far you got in no time is nowhere. So it'd be 0/0 every time. So that's the same number every time. And whatever number it is, it's a crazy number and it's not the one we're looking for. So that's too simple. So what do? We say, oh, from here on in, instantaneous velocity, the precise but conceptually more difficult quantity, v without a bar on top of it, is from here on in defined to be average velocity taken to the limit as t approaches 0. So what I want you to write down in your notes, like I wrote it one way right here. I know this scratch mark is just confusing people. It right here one way. I want you off in the margin to write it another way to see the progression of this thought process. What I'm saying right now, like right off in the margin somewhere in your notes, v without a bar on it, v triple equal sign, limit, like LIM, of t approaches 0, like just like I have here, but then in parentheses, write somewhere else, just write in parentheses v bar and end it, and then end the parentheses. Like before you write anything, like just write that. What I'm trying to say is I want you to see instantaneous velocity is average velocity shrunk down to the limit. In other words, it's average velocity over an interval between 2 points that is so small. It's as small as it can get. It's an interval between 2 points for which the 2 points in time are so close together that they're as close as they can be, or as close as we can conceptualize, without actually being 1 point. Now, if that sounds weird, I'm going to actually define that better in a minute, but you've heard of limits before. Here are limits coming into action. This is calculus coming into action. We're saying if we said it, if it's 2 literal points that are separated by a finite space, that's too big. That's average, and it's not going to be precisely correct for a given moment. But if the 2 points get so close together that they're literally 1 point and there's literally no time, that's too small, and we get 0 over 0 every time. So we're going into the nether. We're going into this weird zone that sounds like not math. It sounds like black magic, I know, or it sounds like some weirdness, but it is math, and I'll explain that more in a second, and it's certainly science. But what I'm saying is, instantaneous velocity is just average velocity, but taken to the limit as the 2 points in time are as close as they can possibly be to each other without literally being on top of each other. So instantaneous velocity is the limit as t approaches 0 of average velocity. And then I'm going to explain more of the limits thing in a second. But now I want you to write one more thing in your notes. Note, there's just 1,000 different ways to say this, so you could hopefully if 2 out of 3 of them jive with you, then that will help a lot. Because another way you could write it, and we're not going to, and from here on in, we're going to write it like the way you see it up here, but I'm just trying to establish it. Another way you could write that is V with no bar over it, triple equal sign, V triple equal sign, limit as t approaches 0 of delta x over delta t. You could write that. That's also true. It means the same thing. If each thing that you just wrote, and if you need me to say it again, tell me and I'll say it again, or play the video or whatever. But I want this to be clear. If each way I just said, if you're like, yeah, I get it, good, that means you get it. Okay, fine. But if you see that they're all the different ways of saying the same thing, then notice this, please. Like delta x over delta t is just a way of saying slope, right? So what we're saying mathematically now is we're saying average velocity is the slope of the straight line connecting any 2 points on a position time graph. Instantaneous velocity is the slope of the straight line connecting any 2 points on a position time graph, but in the case where the 2 points are so close together that they're almost exactly 1 point, right? So it's the slope almost at 1 point. How do we get the slope at 1 point? We draw a line that intersects the curve only at that 1 point, like a line that doesn't cross through the curve anywhere, that just grazes the curve at that point. It's called a tangent line, right? A tangent line, literally by definition, is a line that intersects a curve not at 2 points, but at 1. So for example, if you have a curve that looks like this, the tangent line to the top, the point at the top of the curve, is a horizontal line, right? The slope is 0 at the top of a curve. It's not 0 everywhere at a curve, but I mean at a hill, like a concave down thing on a graph. At the top of it is different slope from everywhere else, but at any given moment, you could talk about the steepness by drawing or picturing a tangent line. And in the extreme case, it becomes clear, like at the top, the tangent line, the only line that will just graze the curve and not crash through it, will be a horizontal line. And that makes sense. The slope of a horizontal line is 0. At the top of a curve, you're no longer going up and you're not yet going down. You're not positive nor negative steepness. You're 0 steepness, right? That example. So if average velocity is the slope of the line connecting 2 points, instantaneous velocity is the slope of the tangent line at a point, graphically. When we switch, so delta x and delta t in math, whenever we use deltas, we mean differences, small but finite difference. I mean, they're usually small, but even if they're small, they're finite we use delta x or delta y or delta x or delta z when we say delta y, it means y2 minus y1. When we see delta x, it means x2 minus y. That means literally the difference between two values of the variable, literally a subtraction, like literally there's a finite actual measurable difference between the two values. We can subtract one for the other, get an answer, right? We use delta when it's a small but finite difference between two variables. Once we take that delta to the limit, once we shrink the difference down so small that it becomes infinitely small, which is what we're now talking about, once the difference between two values of a variable, whether it's delta y or delta x or delta t, once the delta gets so small that it's infinitely small, we swap out the delta and we put in a lowercase d. It's literally, I didn't understand this was going on with the notation until I did. But when we write d, so now look at the top equation. Notice that I took delta x over delta t to the limit as t approaches 0. And then I call that, I said, oh, from here on in, we're going to call that dx over dt. Dx just means delta x in the limit as t approaches 0. And same thing with dt. D just means differential. Please write this down. I'm not saying you're not, but because I know it's a lot, and I'm just about done. I know it's a lot for me to be saying without me writing it down, but D just means delta, but in the limiting case, in the infinitesimal case. So whereas when it's delta, it's a difference. It's small, but it's finite. When it's a D, it's a differential. That just means a difference that's infinitely small. So dx over dt means infinitely small x, like infinitely small change in position over infinitely small change in time. And that is a number that leads to and that leads to an actual calculable, measurable number. So dx is a differential. dt is a differential. Put one over the other, you're still talking a slope. You're still talking a ratio of little differences. But when you put one over the other, this slope is now the slope of a tangent line rather than a other kind of line. And we call it, as you know, of course, we call this a derivative. I'm saying hello, calculus. I'm saying, in short, what I'm saying is instantaneous velocity is the derivative, or technically the first derivative of position with respect to time. So the link from physics to calculus is that instantaneous velocity is the derivative of position with respect to time. I'm saying with respect, like the dependent variable, the rise is position. The independent variable, the run, is time. So that's how you speak about derivatives, right? And so I'm first of all saying that's the link from physics to calculus, but I'm also saying, do I believe that all of you love calculus or have mastered calculus? No, I don't. Do I believe you've seen this stuff before? Yes. This is not your first time around the rodeo, but you may still be uncomfortable with it or not like it. I understand all of that. So I'm saying here's where the calculus starts coming in. If you want to refresh anything now, start refreshing definition of the derivative, mean value theorem. Don't get all caught up and intimidated by like quotient rule and things like that. Like those things will, as we need them, we'll redevelop them. And some of them we don't need. It's not about solving super hard technical specific exercises in calculus. It's about starting to see what the fundamentals of the calculus were all about conceptually. It's about definitions and original theorems if you're going to refresh anything. But I'm also saying to you that in this course, well, I am saying by the time I get to 204, you're like, we really need to do calculus, like integrals and everything. Like it's heavy calculus in 204. Here, it's a warm-up. Here, what we do is we're trying to tie the concepts of calculus together with the concepts of physics. It's not grinding the crank a lot. Like, for example, even this equation that I'm trying to explain right now, you're not going to like use it algebraically. You're not going to plug into it and stuff like that. It's a signal saying what's happening from here on in when you want to think about instantaneous velocity. You got to think about it as a limiting process. You got to think about it the way as a slope of a tangent line. You got to think about it as a rate of change at a point rather than between 2 points. And calculus applies. I haven't told you yet how to apply the calculus, but the issue of calculus and physics is knowing when to use it and how to set it up. So one thing I'm trying to reinforce right now is when you say dx dt from now on, or just like in math class, you say dy dx, you've probably just packaged. Well, I don't know what you've done. When I was a student, I just like clumped it in my mind or lumped it. It's like dy dx was the derivative. And if I didn't like writing it down, it seemed annoying to me. So I often wrote f prime or something like that. But no, dy dx is the right thing to write. It's not just an arbitrary lump that's just being memorized or made up by black magic or white magic. It's dy, like dy dx really means delta y over delta x taken to the limit. It just means slope. It means average rate of change, but over an infinitesimal interval. If you look at that original definition of derivative that you had in calculus, if you were like me, you just memorized and like used when you were forced to, but it didn't. Remember that original definition? You don't have to write this down, but just see if you remember this or if it's familiar or if it gives you a headache, a trauma response. Like limit as h approaches 0 of f of x plus h minus f of x all over h. Remember that? Or a better way to write it, I think, limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That was nonsense to me too for a long time. It was gibberish. But if you look back at that definition, I want you to see, if you stare at it long enough, what it's just saying, that definition of the derivative is just saying slope. It's just saying y2 minus y1 over x2 minus x1, but all taken to the limit as x2 minus x1 equals 0. That's what we're saying here in physics now. Okay, so I know this is like, mathematically, I'm saying, if we have an equation that I've tried to establish here right now, it's that in the end of the day, instantaneous velocity. You want an equation for it? It's dx dt. It's the derivative of position with respect to time. How do you like get it? How do you solve for it? How do you compute it? Well, you got to use calculus, and it depends on the context. Like, we'll practice it. It's not a plug and chug thing, but conceptually, you got to know that how do you picture it on a graph or in a math class? Velocity is the slope of the tangent line to of the tangent line to a point on the xt graph. That's what I'm saying. Now, I'm going to say one more thing. This is a mouthful. If you're really trying to follow me, and again, the mistake that you could make in any of these calculus talks or these calculus rants, the mistake I don't want you to make is to either A, go, oh, okay, I already know calculus, I'm good, I don't have to listen to this. That would be a mistake, I think. In many cases. But the bigger mistake is go, oh, calculus, I was never good at calculus. I got through it. I got my grade, like what, like, okay, calculus and me and not friends, not go, no simpatico with the calculus. No. I'm talking to you. If you're the person that does not like calculus or feels like you were faking your way through, or you got lucky or whatever, and you want to be done with it. No. I'm saying the good news is I know like you're not alone. The good news is I too took 3 levels of calculus in college as a physics major, and I had no idea what was going on with derivatives. I was totally faking with derivatives, much less integrals. Oh my God. And I knew I was faking it, and it was scary. But eventually I got it from the physics, even though it was required for the physics. It's like that. It's a helix. It goes round and around. It's like practicing scales on the piano, and then you need a little actual song to make the scales come alive, but you need to know your scales to make the song work. Like you go back and forth, right? You got to give yourself a second chance on calculus, and it comes through the physics if you stay with me, especially if you go from 203 to 204. Like 203 will be the soft rise. So right now what I'm saying is, yeah, this is a derivative, but don't say, well, I don't understand derivatives. I'm saying you might start understanding them now more if you think of them this way, might. So the one thing to understand about them is that they all hinge on limits. The real hook of this whole deal is the concept of a limit, which of course everybody starts with in calculus class, and it's a total turnoff to almost everybody, no matter how great the teacher is. It's like really hard to care about limits at the beginning of a calculus because you don't know where they're going, you don't know why you're supposed to care, and they don't seem like math. Limits seem like a total like exactly whatever anybody did like about math, precision, predictability, clarity. Like limits are like, what? Now we're like, it is, but it isn't, but it isn't, but it is. It's a dessert wax. It's a floor topping. Like what? No, Oh, well, I'm here to say something about limits, and then I'll go on. Forgive me, but if you fuzzed out on derivatives, it may well be because everything else you understand. You understand slope, you understand average. And so now we're throwing the limit thing in. So was ist das Limit? The limit thing you may have turned you off because it doesn't seem like math, and it might turn you off even more, or in a different way. If you accepted it as a math thing, but you were like me, like, all right, I'll do it in a math class, limit, delta, epsilon, proof, yada, yada. But like now you're in a science class. So you were like, okay, well, now at least we're about the real world. Like, put aside these like Euclidean points and these infinitesimal planes and these idealizations of square root of two. Like, now we're in the real world. So now things like are observable and measurable and concrete and in space and time. So like limits, like that is so not real and not concrete. Like, how does it? Here's the answer. Or here, fair enough. I hear your cry. Maybe you didn't even know that was your cry, but maybe it was. My point is actually limits start making a lot of sense to me when I think of them in a scientific way. Write this down, please. Write the following down, please. In the limit t approaches zero, like that symbol, limit as t approaches zero. So write that down or write it in English. The limit as t approaches zero means the time interval is bigger than zero, but smaller than the threshold of measurement. I will say that again. The limit as t approaches zero means a time interval. So this is in the case of t being time, but this ultimately what I'm saying would apply to any kind of limit. Limit as time approaches zero means the time interval is bigger than nothing. Like there is a time interval. The time interval is bigger than zero, but below the threshold of measurement. Let me expand on that now. But that's a big deal. That means this is not a BS. This is not like some I mean, it's weird, but it's not imprecise. Let's talk quick. And I know I'm watching the clock. But as an example, the whole business when the police officer pulls me over and says, you need to own up to how fast you were going right at that moment when you passed the school zone sign. Like you may say your average over the last hour was 20 miles, and that may well be true. But you also admitted you were at a rest stop for like 45 minutes of it. So you were putting in a lot of zeros into that average. And that shows if your average was 20, you were going a heck of a lot faster than 20 at some point in the journey. And I'm telling you, that point was right at the moment you passed the school zone sign, you were going 85. I don't care that your average for the whole, like, and if you made a graph, you're like, yeah, fine. The slope of your straight line might have been 20. But at that moment that we're talking about, the curve was like was way over here, way above the straight line. And then it came down again or whatever. So the police officer is saying, I have knowledge and concern about how fast you were going at a moment, at a point on that graph. How is he saying that? How is she saying that? Like, how did, I mean, what did she do calculus to pull me over? Like, no. I mean, in a way, her machine did. But what did her machine do? What did her radar gun do? What her radar gun did was it took an average. It did take an average. It was like there's like a beam of light that's going across the road, and my front tires. I mean, this is one example. There's many ways to do this, but like one simple, and you'll do this in the lab. You'll do a version of this with photo gates. Like it's totally like a doable, visualizable thing. There's a beam of light that goes across the road, and my front tires cross the beam of light and close a circuit or start a circuit or whatever. And so like a timer starts going, and then the back of my tire, then my rear tires then go through the light again. Or even, I mean, there's different ways to do this, but basically you can get a circuit to go on and then a circuit to go off when my front tires go through and my back tires go through. Or honestly, you can even do it with just one set of tires, and you'll see that in the lab. But basically, they take how far I've gone, in an extremely small time interval. Like they do take an average. Like the radar gun is not like literally doing calculus. It's doing a calculus concept. It takes an average. I mean, it takes a distance, a measurable, tiny, tiny distance, and divide, like between my two tires, let's say, and divides by a tiny, tiny time, the time interval between my two tires. Now it's tiny, like milliseconds, right? So it divides, so it takes an average in principle, tiny speed distance divided by tiny time. But here's the hook. Here's why we're calling it a limit. Why we then say that's how fast you're going right now. Why we're saying that's small enough. That's not zero, but it's close enough to zero for us to call a limit and to say that's what we're going to put as our. We're writing down your speed right now was 85. Why they can do that, why we can call this a limit is because back up to what was problematic about the whole problem with using an average to describe what happens at a point is that things are changing from points to point, right? Like an average is fine if the whole graph is a straight line, if there's no variation at all, if the car was always going, like our first problem in homework 4, if the car was always doing the same thing, then for sure, if you take the total distance divided by the total time, like 20, then 20 is right every single moment. It's because the car is changing its speed that average does, because the curve is not a straight line, that average isn't the same thing as instantaneous. So what they're doing is taking an interval of time that is so small that everybody knows that any amount of variation that could have possibly happened during that time interval, like during that time interval that they kept, like the milliseconds, maybe I was going like 84.9 and then 85 and then 85.1. Like maybe there probably was a little bit of wobbling, a little bit of variation because the curve isn't perfectly straight. But the point is that the interval is so small that the deviations from that value are too small to be measured, too small for anybody to use in court, me or them. Like in other words, even if I go up and claim you just took an average, you didn't take the instantaneous, and they're like, so what's the problem? I'm like, well, my instantaneous could have changed during that time. The point is, there's no way it could have changed from 85 to 20. It could have changed from 85 to 85.2 or something, but whatever it changed from is super close to 85, and it's so close that literally neither I nor they could put a measurement on it. And if you like, we don't have tools that precise. So if you can't put a measurement on it in science, it's meaningless. That goes back to Galileo's principle, form number 2. If there's no experiment, or if there's no data that shows it, then it might be philosophically fascinating. Maybe it's even mathematically fascinating, but it ain't scientifically real, right? So what limit means in science just means we've squeezed the interval down close. We've left the interval big enough that something happened. It wasn't nothing. Something affected space and time and is affecting our measurements. But whatever happened was consistent with whatever happened was in such a small interval that it was had to be so consistent with that interval that even if we try to measure the inconsistencies, we don't have measurements precise enough to capture them. So we can say, aha, that is the limit. That is 2 points being as close as they can to being one without being one. They're so close that their separation or the significance of their separation is beyond our ability to measure. Therefore, it's not scientifically meaningful. That's what limit means. It means small enough that the deviations are immeasurable. Therefore, the value is meaningful. I hope. So from now on, if I ever say limit, or if you ever hear limit in my calculus class, think of it that way. It's not unrealistic. It actually is us being super realistic. We're saying, dude, there's a limit to how we can measure. So like fall below that, still stuff is happening, but it's not nothing, it's not zero. But if it fall below that, we can't quantify it. So the limit, by limit, we mean we mean measurement threshold. So that's a lot. I'm just trying to bring the physics and calculus together for you. I hope that makes some kind of sense. I'm going to go back now to homework 4 and be concrete and very pluggy chuggy now for the next 20 minutes. So I'm going to switch gears. I'm going to screen share now to show you I'm switching gears. We're going to go over where we're going right now. But tell me while I'm doing, just please raise your electronic hand if you're still vaguely with me, if that did it, or if you had any, or private chat if you had any questions. Yeah, great. Thank you, Gabriella. Awesome. Thank you, Sydney and Emmanuel. Okay, great. I see like 12 people. Great. I'm not going to name you. Awesome. I appreciate it. You're being very patient. So now we'll get concrete. I have to share. So we're going, just so you know, and for the purposes of the recording, we're going to this now. Yeah, number 3. Excuse me. So this is the homework we're talking about. We're going to number 3, the one on the board. Okay, so I'm going to have a little bit more. So now what it sets up, oh, there's Emmanuel. Oh, awesome. Sorry, I've been like yammering so much. I haven't been looking. Thank you for showing video, Emmanuel. It really means a lot. And for raising your hand. Okay. Notice this equation now. So the homework establishes this equation. It's the second equation. Like, so I've just been yammering for like minutes and minutes about the first equation. So now it brings us to the second equation. Notice here I'm writing it slightly differently from the way I did on the board. I want you to be fluid between the two. Either way, we're now saying, so this is now an analogy. Like average acceleration is now change in velocity per time. Average velocity was change in position per time, which we call displacement per time. So average velocity, V bar, triple equal sign, change in X over change in T. Now we're saying A bar equals change in V over change in T. Just notice the pattern. Both equations have the same structure. On the left side is a bar, always an average. We're defining averages on the left side, but we're defining the averages as values that represent intervals between particular points. So the right sides of the equations don't have bars on them. Like that's not a typo and it is significant. Right. So last thing I'm going to say about this. So like average acceleration is like the speed of the speed. If you want to shorthand intuitive, like average acceleration informally is the speed of the speed. It's the rate at which the rate is changing. It's the change in the change. Um, um, if you were making like a Miller's analogy out of it, like for SATs, I don't know if they still do that, but they used to. Like you could say in your notes, average acceleration is to velocity, like average acceleration colon velocity, colon average velocity is to position. You see what I'm saying? Acceleration is to velocity as velocity is to position. It's the same relationship, just hiked up a level of change. Therefore, the last thing I'm going to say about it is that if you followed at all any of the calculus I was just saying, trying to say, if you get that V is defined as dx dt, actually, I'm going to write this then. Here, I'm going to transition to the, okay, I'm going to switch the screen share now. But you notice, or no, you don't. Wait, I'm screwed. Oh. So what I'm trying to establish now is the second equation on the front sheet of that was up on the board. And now I'm going to, hold on. I forgot how to add a page. Hold on. Bear with me for a second. Okay. Um, okay, I'm going to switch the screens. So we had this, right? Like everything I've just been saying was about the top equation. Now I'm trying to get into the second equation, which is based. So we had to establish the first one to get the second one because the second one, I don't know why the circles disappear, but the second one uses V's without bars on them on the right-hand side of it. So we needed to establish what V without a bar was. But so now what I'm saying, If you're following this at all, we're trying to make the connections. I'm saying at the end of the day that velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. So acceleration is the derivative of position with respect to time. It is the second derivative of position with respect to time. Velocity is the first rate of change. Acceleration is the second rate of change, if you want to think about it that way. It's the slope of the tangent line on a VT graph. And notice the way second derivatives are written. It's written d2x dt squared, not, and that used to be another thing for me. It was like, oh my God, why are they writing it that way? Like, that's just it's another thing I'm just going to memorize. Like, math makes no sense. But no, it does make sense if you give it the benefit of the doubt and take it seriously. Like, it's not derivative times, it's the reason the twos are written in funny places is because it's not derivative times derivative. It's derivative of derivative. It's the rate of change with respect to time of the rate of change with respect to time of position. So velocity is the first derivative, acceleration is the second derivative. Let's get to the home. So now let's do to a plug. Now this plug and chug we're going to do is going to be a comfortable breathe out. Like I promise you. All that said, that's how I want you to conceptualize this. Now running the numbers is not often this hard. Run the numbers. Let's go to problem number 4. I mean, to homework number 4 to problem number 3. I'm not doing the 5-step method. I'm just giving answers here as it's at the top. I'm just trying to get to the point finally. So we have this like Toyota or something that goes from 0 miles per. So I'm at homework 4, problem 3. We have a Toyota that's going from 0 to 60 miles per hour in 2 minutes. Notice what it doesn't tell you where it gets to. We have no idea how far it gets at all. It's just telling you how its speed, its velocity changes from one moment to the next. So it goes from 0 miles per hour to 60 miles an hour in 2 minutes. What's its average velocity? So I'm just plugging into the definition of average, what's its average acceleration? So I'm just plugging in to average acceleration. And I'm not even messing with the units because the units it's asking for in part A, it's asking for miles per hour per minute. Okay, so if I just keep the units the way they are, I get 60 divided by 2, 30. I know it's all kind of illegible, but it's just 60, as you might think. It's just 60 divided by 2, which is 30. 30 watts. 30 miles per hour. 30 miles per hour per minute. Now, maybe that's awkward to say. Maybe you think it sounds unscientific or something. We'll get to the more scientific sounding thing in part B. But first, I'm doing it this way to show you like this is legitimate. It's not customary, but it's legitimate. And to me, it actually makes a lot of intuitive sense. It's trying to express like what an acceleration. An acceleration will always have 2 references to time in it. They don't have to be the same units of time, but it has to make 2 references to time. And technically, like miles per hour. Notice miles per hour means like per always means divide, right? So this is 30 miles per hour per minute. Like both the hours and the minutes are in the denominator. What are we trying to say? And it's okay that they're not the same. What we're trying to say here is every minute, this car increases its speed by 30 miles per hour. We're not saying every minute it traveled 30 miles. That's not what we're saying. Well, I have no idea at this point how far it traveled. I'm just saying every minute it increased its speed by 30, and speed is always already, or velocity is already measured in miles per hour or some kind of time unit. So every minute it gained 30 miles per hour. So that means 30 miles per hour per minute. There's 2 references to time. There have to be if it's acceleration. And I think when the references are different like this, you can almost picture what's going on. Like again, so if you've ever driven a car or you're picturing like a speedometer of a car, like old-fashioned ones, like had needles that pointed to different numbers, we're not talking about the number that the needle's pointing to. We're talking about how fast the needle's going, right? It's speed of the speed, if you like. So 30 miles per hour per minute would be the average acceleration for this answer. But then now, okay, there's a more scientific or a more customary way to deal with those units. So it asks you in part B to convert the units to miles per second squared. Now, first of all, if we want to be even better, we'd convert them to meters, but that's not even, we could do that. We could divide the whole thing by 1600, or multiply the whole thing by 1600, and then we'd have it in meters. We're not bothering. But we are going to convert the hours to seconds and the minutes to seconds, because what I want to show you is, yes, customarily, acceleration units are written in distance per time squared. I want you to see squared is just a notation. Well, it's not. We're not squaring time in some psychedelic Michael J. Fox flux capacitor way. We don't mean we're not making time two-dimensional. We're just saying that it's divided by time twice. There's time in the denominator twice. So technically, there's 2 units of time being multiplied by each other in the denominator. If they're the same, we could just call it squared. So that's where the squared comes from. So we could write this whole thing in miles per second squared. So traditionally, we consider meters per second squared. So whenever I use square brackets from here on in the class ever, square brackets means I'm talking about units. So the units of velocity from now on are meters per second. The units of acceleration are meters per second squared. And just to get an answer here, we're going to convert just once. We're not going to do a million unit conversions in this class, but just to get it in practice, we're going to do one right now. We're going to convert our 30 miles per hour per minute into some number of miles per second squared. Now we're gonna do it together. Question is, what I think is good with unit conversion. And look, again, I think unit conversions is like anything else, like calculus or anything else. If you're like me, you probably hated them when you spent a lot of time on them at the beginning of chemistry. It's like actually really important and really fundamental, but it's like really weird and abstract and boring. And no matter who the teacher is, like we don't ever appreciate these things until we're using them later. Like it's just always the way it goes. So some of you still might hate unit conversion or think you don't know how to do it. So here's now my physics perspective on it once that might clean it up for some of you. And those of you who don't need it, I apologize for the redundancy. The way I think of unit conversions is, first of all, I always try to ask myself in advance, do I think the number should get smaller or bigger? I use that as a back checkpoint to make sure I'm doing it right. Like we're converting from miles per hour per minute to miles per second. We're asking like how much change occurs in every second, not in every minute. So I ask myself, should the number get smaller or bigger? Raise your hand if you think the number should get bigger. Please raise your electronic hand or send me a private chat. Okay, good, honest. I appreciate it. Thank you for paying attention. Awesome. Awesome. Now put your hands down. Now raise your hand if you think the number should get smaller. So okay, I'm going to repeat. I'm going to want everybody. There's a checkpoint. I'm going to repeat the question. I want everybody to rate. I don't care if you're right or wrong. You can get points either way. In fact, you get more points if you're wrong, honestly, right? With the portals. But I want everybody to participate. Like raise your hand for one vote or another. I'm going to repeat the question. We're about to convert. We're going from A to B. If you've done the homework, you just like look at your answers if you want or whatever. We're going from A to B on question 3. Okay, thank you, Alfred. That's helpful. Thank you. And also, I'm not forgetting what Alfred said before, too. I'm like freaked out by it, but I'm not forgetting it. The question on the table is, we just wrote that this car, we're given a situation, we said this car is it's gaining 30 miles per hour of speed every minute. Now we're asking, how many miles per second? How many miles per second is it gaining every second? That's what we're asking now. Same situation, just asking different question. So I want you to think about just intuitively, should it be gaining a lot more miles per second every second, or should it be gaining a lot less, like as compared to hours and minutes? Do you think it gains a lot of speed in a minute and a lot more in a second, or do you think it gains a lot in a minute and a lot less in a second is basically what I'm asking. So I want you to vote either way. Do you think the number that we're about to get in B should be big? The two choices are bigger or smaller than A. Raise your hand if you, and I don't care if you're wrong. In fact, again, it'll show me that you're paying attention and you're trying. But I want you to vote either way with an electronic hand. Is our answer to B, should our answer to B get bigger than our answer from A? Raise your hand. 1, appreciate the honesty. And the other person changed their mind maybe. Okay, fine. Thank you for the honesty and the participation. Great. Put your hands down. Now raise your hand for smaller. Okay, a lot more. And thank you for the participation. And I think, okay, great. Okay, before I'm pleased everybody's participating. Great. Now put all your hands down. Thank you. Now raise, now put all your hands down. Oh, someone else. Okay, now put your hands down. Now, and put your hand, thank you. Now, last thing, just to control the experiment. Raise your hand if honestly you did not raise your hand. Be honest. Raise your hand if you didn't, for whatever reason. I won't challenge you. I won't put you on the spot. I just want to know. Raise your hand if you hear me speaking right now, but you didn't vote for either of the other two. Just everybody. Oh, okay, that's on it. Oh no, you did. I think so. Not okay, okay. So you're raising your hand because you're paying attention. Okay, I think you did get everybody. All right, that's good. All right, thank you. I think everybody. Okay, okay, that's good enough. Okay, okay, put your hands down. And you can all get points for that. Thank you for hanging with me. The answer is yes. I think the number should get smaller. I do think the number should get smaller because we're looking in seconds now. Like how much could really happen in a second compared to a minute or an hour? I think it can get smaller. But now let's do it. That's just that's my thing in my back of my mind to check because now we're going to do the unit conversion. And here, everybody, a lot of people hate unit conversions. I would wager that most people they know. Usually, people in chemistry they know it involves a conversion factor, and they even usually know what the conversion factor is. But they just never. I was always like, I know the conversion factor, but I can never remember whether to multiply or divide. Here's how I do it. I always multiply. I'll show you how. I always multiply. I always multiply by the conversion factor phrased as a 1. The reason I'm always allowed to multiply is as long as you multiply by something that equals 1, like 4 over 4 or 3 over 3 or x over x or 60 minutes over an hour, right? 60 minutes is equal to an hour. So it's like x over x, it's 1. I always multiply by a well-chosen 1. A well-chosen 1. It's like Neo, the well-chosen 1. I always multiply by a well-chosen 1. How do I choose? And the choice is a conversion factor. All I have to choose is whether to write it upside down or right side up. How do I choose that? Just by looking at what units have to cancel out. Here's what I mean. We have 30 miles per hour per minute. I've got to multiply by so first of all I'm going to do I want to get rid of those minutes. I have to convert minutes to seconds, right? And if I'm boring you, I'm only going to do this once, but I think some people need it. I want to cancel out those minutes and turn them into seconds. I want to get rid of those minutes and I'm looking at the minutes first because it's easier. I could have looked at the hours first, but I'm looking at the minutes first. And multiplication is commutative. You can do it in any order. So I'm looking at the minutes first. So how many seconds? And I want to change minutes to seconds. So how many seconds are in a minute? 60 seconds are in a minute. So my conversion factor, I'm going to multiply by 1. I'm either going to multiply by 60 seconds over 1 minute or I'm going to multiply by 1 minute over 60 seconds. Either way, in my mind, I'm thinking of it as multiplication. And it's 60 because there's 60 minutes in a second. The only issue is which way do I write it? So the way I solve that issue is I put the minutes wherever they need to be to cancel out. I put the minutes of the conversion factor wherever they need to be to cancel out with the original minutes. I don't want minutes anymore. I want them to cancel. So since the minutes are in the bottom of the original number, I put minutes in the top of my conversion factor. So I just write 1 minute over 60 seconds. I'm allowed to do that because 1 minute does equal the same amount as 60 seconds. So I write 1 minute over 60 seconds. I don't even think about whether I'm dividing. I multiply, that's what I write. And I cancel out the minutes. Also in the back of my mind, I'm like, oh, the 60, I'm multiplying by 1 over 60. Really, technically, someone could say I am dividing. So I think the number is looking like it's going to get smaller because the 60 is on the bottom. So I think I'm doing a good thing. Like that's my check in my mind. But the point is, I chose it to cancel out the minutes. Then I do the same thing again with the hours now. I want to cancel out the hours and end up with seconds. So I think how many seconds are in an hour? Now, I do this in my head, I go, well, there's 60 seconds in a minute and there's 60 minutes in an hour. And in my head, I go, well, 6 times 6 is 36 and there's 2 more zeros, so it's 3,600. Maybe that's too much for you. Maybe you want to break it up into a couple of steps or send me a text or an email. Fine, fair enough. But here, I'm doing it that way. I'm saying, look, I could, or do it out on a calculator. And believe me, there's 3,600 seconds in an hour. That's the conversion factor I need because I need to get rid of hours and I need to be left over with seconds. So I put 1 hour in the top again. I put 3,600 seconds in the bottom. And so the minutes cancel out. The hours cancel out. I'm left with seconds and I'm left with seconds again in the denominator. So I have seconds squared in the denominator, and the miles, like nothing ever happened to the miles. They've just been sitting there the whole time. So my ultimate answer is going to be in miles per second squared, it's going to be 30 over 60 times 3,600. Like that's what it is, right? And it makes sense. I'm putting a humongo number on the bottom. So my whole thing is going to get like much smaller. So it's 1 over 7,200. How did I do that? Think of it 30 over 60 is 1 over 2, 2 times it, whatever. You can do it on a calculator. You'll see. But like the 30 over 60 reduces to 1 over 2, and 2 times 36 is 72. But so 1 over 7,200 miles per second squared. If you actually left it like that, I wouldn't object. That's fine. That's like a reasonable physics number. But if you want to really, or a math number, but if you want to write it as a scientific number, the final answer is average acceleration. Average acceleration for that interval equals approximately 1.38 times 10 to the negative 4 miles per second squared. Very, very small number, but that's the answer, right? Like that. Okay, I got to move. It's 122. I'm going to make tracks here. If you have questions, let me know, but I'm going to move on for the next one. Number 4. Here's the answers right here. Look at them. So it asks you to choose a coordinate system, like whether east is positive or negative. You could choose whatever you want. It's a choice. If you chose the same choice I did, which I recommend, you'll get the same answers I did. If you chose the other one, that's fine, but then all your answers have to be consistent with that. They all have to be the reverse of what I have, if that makes sense. So these are the answers for B and C. Just stare at them for a second. If you want me to go back or you want to slow down the video, please do. Because the point of it, well, and then here's the answers for the accelerations. The purpose. Did I skip one? Or did... Somehow I skipped. Oh. Oh, I do this every year. Sorry, it should be 4, not 40. Sorry. The other class didn't catch it. I do that every year, but okay. So just notice, we have 7 minutes left. Notice there's 2 cases of positive acceleration, 2 cases of negative acceleration. The summary of this problem is that acceleration means change in velocity. Okay, and some people ask me about this from the videos and stuff. I'll say this more of this on when next time we have class, but and I don't think there's any homework to anyway, whatever. I'll make sure the homework is right, but I think it is now. But acceleration means change in velocity. Velocity takes into account direction, positive and negative signs. So a positive acceleration means a gain in velocity. It means the velocity numbers, whether they're negative or positive, are trending more positive, are getting bigger. And a negative acceleration means the velocity numbers are getting smaller. Physically, what that means, you have to be very careful. Positive acceleration does not necessarily mean speeding up. It means either speeding up while you're traveling in a positive direction or slowing down while you're moving in a negative direction. Because if you were moving in a negative direction, your velocity numbers are all negative. But if you were slowing down, they'd be going like negative 40, negative 30, negative 10, right? The numbers would be getting lesser, but the velocity numbers, negative 40, negative 30, negative 10, negative 10, they're getting more and more positive, right? So you're slowing down while you're moving in the negative direction. That's called positive acceleration. Why? Well, because of what I just said, but also if you kept that up forever, you'd eventually hit velocity 0 and then velocity positive 10 and then velocity 20. So positive acceleration means eventually you'd be going positively and eventually you'd be speeding up, but you might not be right now. You might be now slowing down in a negative direction because positive acceleration ultimately means you're being pulled progressively in a positive direction. So positive acceleration means speeding up in a positive direction or slowing down in a negative direction and vice versa. Negative acceleration does not necessarily mean slowing down. It means either slowing down while moving in a positive direction or speeding up while moving in a negative direction. That's the summary of that. Again, let it sink in. You can ask me questions. We'll go back to it. And then finally, okay, I'm going to leave it at that for now. The main goal we have to get to next class is the very last problem. The big problem 6 is super important. We'll spend we'll pay attention to it, and then we'll move on to the next homework, and I will readjust the homework deadlines if need be. But since we have like 4 minutes left, I'm gonna end on this. Don't go anywhere, please. I'm gonna like the physics, I'm pausing. And I'm okay, I'm pausing on this. I'm taking into account what Alfred said. I'll readjust things, blah, blah, blah. But I'm stop. Don't go, but I'm stopping the recording.